ashamed for this. So I'm going to talk a little bit about the research that we have been, at least part of the research that we have been doing the last maybe 7, 8 years under, focus on many different applications, but today I'm going to focus on one of the main applications that we target, which is collaborative autonomy, and in general, computer vision. Oh, wait, something happened, which is bad. All right. No. Oh, that's the problem of having this first slide being your last slide as well. All right, so Amlan already introduced myself. This is my research group. At least it's a 3D scan, a LiDAR 3D scan of my research group. Again, everything that I'm gonna talk about today is, of course, the work of all my PhD students, master students, undergrad students. We have an amazing group. You see here actually a little bit one of my PhD students doing this. Again, he's one of our most enthusiastic people in the lab. Just to show that, again, we're going to play a little bit with sensors and sensor data as a use case for what I'm going to talk about today. So in general, the question that we target in this domain is how can we build resilient and efficient real-time data analysis for mobile systems in challenging environments, in contested environments. It takes different meaning in different applications. And again, just to mention, today I'm going to focus on collaborative autonomy and autonomy, computer vision, but we have the same issues in healthcare domain, in smart grid, in energy systems, in infrastructure level control as well. But again, all at different scales, maybe slightly different version of a problem, but you still have the same macro issues up to some degree. So to build this kind of system, so a system that can process in real time data in resource scarce and challenging environment, you need to face many different challenges. And in my group, I think we try to have a very broad perspective on what the solution entails, which is algorithm, the computing strategy, the communication strategy, and the infrastructure level as well, right? So starting from the algorithms need to be optimized for operating in environments where you have very little computing power, very little communication capabilities. I'm going to explain what that means in an application. So you want to redesign this algorithm, rethink what machine learning algorithm is to tailor them to this kind of collaborative, low resource environment. But of course, as you move up the chain, you have a device problem, like how I compute. Do I compute myself? Do I offload the computing process to somebody else? Do I have enough reliability to do this? How do I strategize in terms of what's going to happen? And also, what do I need? Because some processes are definitely real time, super real time. Some other layers of autonomy are, you have a little bit more time. And so you want to strategize in terms of the system level state, but also in terms of how, the semantic meaning from an application perspective. And of course, then again, I'm a telecommunication engineer by training. You have a communication problem. So how I communicate, how do I build, I interlace the different components of a system in a way that makes sense from an application point of view. So beyond the traditional communication paradigm that looks at traffic, now we want to look at data and what that data means in terms of operations of a system. And then you have a whole infrastructure level control problem. So if I have 5G system, I have communication resources, I have computing resources. One problem is how can I slice my resource? So from a communication perspective, from a computing perspective, to serve different applications, different groups of devices. So there is a whole 5G/6G problem in terms of embedding AI algorithms that look at what's happening and optimize the system. And here again, there is one paradigm shift, in my opinion, that goes from just data and traffic volume to actually what the system needs. And that also means thinking about data and application state, or from an autonomous vehicle perspective, how difficult the mission is. Okay. So just to show people that we don't do this only in theory. Definitely there is a theoretical component in terms of machine learning design, in terms of optimization, but we really take as a starting point actual systems. We spent an enormous amount of time building edge computing for drone system, for rovers. We now have a whole series of small to big drones that we test with. We have our autonomous rovers for indoor, outdoor navigation, and we collect real data. And I can tell you that even if this took an enormous amount of time, again, I built a statue of the first PhD student that developed the drone, the middleware for drone flight. Like there is a statue of David holding a drone like out of the lab, but it was 2 years of work to build this whole interconnected system. But we see really interesting things that are illuminating our path to build a system that actually solves problem and not just do something in theory. And we are expanding this to use more sophisticated communications technologies using multi-user MIMO, multi-antenna. So in that case, we have a little bit more flexibility controlling, for instance, how much bandwidth you use, how you parallelize, how you packetize information and all of this. And we are expanding our ground autonomy capabilities, building also rovers that are capable of sensor fusion and so on and so forth. Just to say again, what I'm going to show you, even if I don't tell you so, has been deployed on rovers and drones, and it works up to academic degree. But and now I'm a founder of a startup too, and I can tell you that a lot of this works in real life too. But again, I'm going to show you some academic perspective on this. So some examples, and I'm going to take one of the environments that actually is a really good fit to this, which is defense. And so you're going to hear some terminology, see some pictures that are slightly militarized, but that's because of the environment. So think about this, right? So why collaborative autonomy? So you have an autonomous or semi-autonomous vehicle. So you have something that can process data, can from multiple sensors, typically camera, LiDAR, radar. That's a very heavy actually process by itself, even for big vehicles. And then you have AI algorithms, so perception and control, making sense of this data. And again, if you have 3 LiDARs, 6 cameras, that becomes very fairly heavyweight process. So you do have a problem of computational complexity, but you have some problems that are a little beyond that, which is, okay, you have a limited range of vision, or you have outdated or obstructed bird eye view information to navigate, right? And plus, okay, there are some problems from a defense perspective about exposure. When you use active sensing, you expose the vehicle to detection and so on and so forth. So one possible way to solve this is by building a collaborative system. For instance, you have some low-cost, attritable, expendable drones that have very low capabilities, right? But from a point of view of operations, if you build that link, right, then you can boost the capabilities of a primary vehicle, for instance, by improving situational awareness, by providing traversability maps, bird eye view maps, information about other vehicles that are present in the environment, and also can reduce operational exposure of a vehicle. Now, the problem is that that drone has extremely limited resources. Okay, that's not what my friends in the industry call like a Gucci, a kind of boutique drone. It's something that you throw it, and if you lose it, you lose it, and that's fine. So you don't want to have $1 million drone that goes and it's jammed and just falls and it's destroyed, right? So the problem is extremely limited resources, computing, memory, energy, all these things. That's also airborne, so it's quite extreme. So you cannot really extract very complex semantic information from the sensors in real time. It's hard to have whatever sensor data you can get there and build a bird eye view map with some friction information to help the primary vehicle, right? And then we also have a problem of what that vehicle itself is doing, which is, okay, the vehicle needs to autonomously navigate typically, or at least up to some degree. So you cannot really have really complex autonomous navigation logic there too. So we have a problem of providing information and also what do we do there in terms of capabilities, right? So one typical thing you can do is also establish some degree of collaboration from a computing perspective, right? So this primary vehicle can help the smaller drone too, but you still have a problem here, which is the wireless link. And again, I'm a telecommunication engineer, and I don't believe in good wireless links. Like there's no good wireless link. Even if you have a best 5G, whatever, you still have volatile, not really controllable data rate. And when you build this kind of loops, you really do want to have some notion of reliability. So, if you have very high frequency, high capacity links, you have hostile propagation environment. If you go low, you have, in any case, impaired propagation. You also have, but if you want to send high resolution data, you end up with a lot of data that travel over, like even the defense environment, exposed channel. That's also a problem. So when we do our measurements, like this is a rover, this is a multi-antenna system with very high capacity, and we look at, on average, things work. But when you look at sample by sample, so image by image, LiDAR point cloud by LiDAR point cloud, you see a lot of variability, and you see all these spikes. And this was, by the way, a very simple line of sight environment. You still see that because of geometry, because of the body itself, of the drones, of the rovers, it's still crazy. I mean, you don't have a reliable link. Okay, so these are the kind of problems that we face. Okay, there are other things that I'm not going to talk too much about, which is how you actually connect the vehicles to human operators. You still have the same problem, actually. How you compute, what you represent. Can I just send videos? Can I send point cloud? Do I need to process? Where process? All these kind of things. And again, apparently, this came as a revelation a couple of years ago to me, that there is no autonomous vehicle without a human operator somewhere that looks at what the vehicle is doing. Apparently, there is no full autonomy. One of the biggest costs for autonomous, even urban environments, is for car companies, autonomous car companies, is operators. And you can imagine that when you take this into, off-road defense setting, you also don't go up in terms of capacity of the system necessarily, so of links. So you have a problem. So it's still a problem from this point of view. So now I'm going to show you a little bit of some of the solutions that we developed from a point of view of how you compress the data and you try to minimize the amount of data that you transfer over these channels. And again, this is very important to deliver the information or to build control loops. I'm going to explain a little bit about how you can make these models dynamic so they become more efficient, responsive to the environment. And if I have time, I'm going to talk a little bit about how you can actually control communications to make them aware of the data itself and the mission itself. Okay. Good. Sounds like a plan. Did I get you on board on the problem? Okay. I work on this for 8 years. I hope it's actually an actual problem. So let's start with compression, right? So you want to transfer some information, right, from one vehicle to another. And let's say you have camera information only. You typically use JPEG and PEG. Everybody says, okay, you can just compress, right? And of course, that's great. But the problem is that JPEG and MPEG are designed for human consumption, right? Not for machine consumption. And when you reduce the quality of JPEG to compress more, the first thing that JPEG does is to blur the edges. And that's not a very great thing for computer vision, right? Now then, so that's ineffective when you want to compress more. If you even go to, so JPEG, MPEG, they're not designed for sparse signal. So if you go into the radar LiDAR domain, which is a sparse point cloud of data, that doesn't work either. If you project the point cloud, the 2D image, you still get points, and that's not good for JPEG. I can assure you, it's really bad. And the other problem is when you use temporal correlation, so MPEG, that's sometimes very efficient, but let's say you have moving vegetation, which is a lot of details of things that are changing frame by frame. So there is very little temporal correlation, and there is a lot of details, and that's where you get a lot of megabit per second rather than a compress, right? It's like when I make these examples in my courses, I say, okay, you can imagine like a fixed camera on a wall, right? And that's very highly compressible, or your Avenger movies with a lot of explosion and stuff that happens all the time, that's not very compressible, right? Because you don't have temporal correlation, you don't have spatial correlation. So it's a little bit of a mess. Now, of course, you have the other end of the solution range, which is autoencoders. So you can use neural models to compress. The problem is that they're typically very complex, sometimes more complex than just doing the computation by yourself. And still, they are allocating, in a way, a lot of complexity and a lot of representation bits to things that are irrelevant. Again, we have that moving background, the foliage. You don't care about that if you are detecting the presence of a person. If you are looking at the terrain, you don't really care about how many leaves you have, what color, if autumn is beautiful or not. I mean, it's just, you don't care. So that's not necessarily a solution. So there is one branch of research that started off with a very, very simple concept, which is, okay, we take a computer vision algorithm, for instance, for object detection, segmentation, and we split it. Okay, like very simple. But you just split it, execute one portion at the mobile device, the other portion to the head model at the mobile device, the other portion at the primary vehicle in this case. Okay. So instead of transmitting the input, I'm transmitting the tensor, which is the output of that first portion of the model. Okay. There is a very famous paper that did this at this point, maybe 6 years ago. That's called Neurosurgeon. And it's very interesting because it shows that the optimal, it's super cited. I mean, it's very interesting to see. The optimal thing to do in this case is to not split. It's very interesting because you are allocating some computing to the mobile device, but tensors tend to be a lot bigger, especially early on in the model, compared to a JPEG image. And so it doesn't make any sense to do a little more work in a weaker device and transmit more. Okay. Actually, there is a very good splitting point, which is toward the end, because the network itself is a compressor encoder. But that means you do most of the computing on board a mobile device, so why would you do it? Right. So it's very interesting. But one very famous paper shows that this doesn't work. And so one of our main contributions, maybe the one I'm most known for, is this notion of a different way of doing this kind of split computing. Okay. And we call it artificial bottleneck, supervised compression. It takes different names. But the idea is that you take the original model, and instead of just splitting it, you modify it. You modify the architecture, you modify the training. The idea is now that instead of just keeping the model as it is, you build what is essentially an encoder-decoder structure within the model. We're not building a separate encoder-decoder structure. We are modifying the model. Okay, so now we have that little bottleneck as early on as possible, and we transmit much smaller tensors. Okay, we split at the compression point, and we try to make that as little as possible. Okay, so you have a multi-objective optimization problem about designing this. You want to minimize complexity on that side. You want to minimize data. You want to maximize accuracy. So it's not necessarily easy to design from a point of view of making this work. But so if you look at what we get at the end, is that instead of just the model, we have a first part, which is essentially an encoder, and a second part, which is a decoder, and then a final portion of a model. Now, you have a distinct functionality here compared to a traditional autoencoder, because the encoder-decoder chain is not trained to reconstruct the input image. It's trained to reconstruct the output tensor of that chain. Okay, so now we are training that first encoder-decoder to support the computing process of this AI model rather than just reconstructing the input. And this is the key. I mean, it's not easy from a training perspective. It's a little easier from an architecture perspective, but this is the idea. So we have a semantic in-model supervised compression, which is trained to make that representation as effective as possible for the task. If your task is to tell that this image is a pizza, that's probably easier than a task detecting 500 different objects And then we can tune the compression for that specific task. But in any case, you don't care about that vegetation thing. You can remove a lot of the details. Okay. You see here an example that I don't know why my student always use when I talk about autonomous vehicle. He puts a lot of birds, pizzas, and things. So don't do that. Don't do that in talks. Makes a little awkward. So again, when you train this model, we have our specialized training methodologies. You want to train this pipeline of things, subcomponent within your model. It's actually interesting that if you just train the model as if it was a traditional AI model, you get really bad results. Even if people show in some papers that it works against, let's say, suboptimal. So maybe you compress more compared to transmitting the input tensor, but it's really hard to beat JPEG with this. Accuracy goes down fairly quickly. So we developed over time multi-stage training methodologies that work really, really well in terms of tuning that representation specifically to the task, refining the model, and all these things. Okay, I'm not going to talk too much about it because I'm a little late. So when you compare this is a slightly more sophisticated version, which is a variational version of that encoder-decoder chain. You want to look at different metrics, right? It's not only compression. You want to care about accuracy or performance of your task. You want to care about how much data you transmit, but you also want to care about complexity that you're pushing to the mobile device, right? So you have a multi-dimensional trade-off. So we are the blue line with the little stars, right? And that you see we have minimal complexity. Again, we use as a proxy just the number of parameters, essentially. We have very minimal complexity. We resist quite a bit better compared to all the other options to compression. And then in terms of accuracy, we perform comparably with a lot of most sophisticated autoencoders that are out there. This comparison includes JPEGs, includes a lot of all the autoencoders, the most performing autoencoders. So this works in a way and works for many different tasks. And we have autoencoders that actually encode for multiple computer vision tasks. We have some specialized encoders. I'll show you a little bit of this. So why does this work? So this is a representation of, just to give you an idea, and again, more birds, dogs, and stuff. But so this is a comparison with the best performing variational autoencoders by Ballet. You see red, it's where the regions of the image where we focus our representation. And you see that we are sort of ignoring the background. We are focusing on some semantic portion that are actually relevant to the task. So we erase a lot of the grass or the background, and the model focuses on what matters to understand the object, right? Depending on the task. So just to show, okay, from a point of view of complexity, I'm not going to talk too much about this, but the encoders are really, really tiny, right? And of course, we went through the process of making them commercial grade up to some degree with like quantizing, making them really effective. And the encoders are really, really small. That's one of the core advantages. Now, so this is one thing. We have been doing this for many, many years in many different versions, but now we are evolving these models in a way that somehow I think also matches the direction we are going toward in many different technology areas. I'm going to show you one recent result that we have in this domain, which is rather than just one encoder, decoder, tail pipeline, is a multi-branch model. So it's a model that provides some flexibility that can tune itself to what's happening at the level of data, at the level of context. Okay, so the idea in this case is very simple. And this is, by the way, is not for image, it's for radar data. So we are proving that this works for 3D data as well, for sparse data and object detection. So again, this is a technique that is not good only for detecting pizza versus hamburger, which is not a very real-time problem, but it works for object detection on radar data, right? So the idea here is that if you make the encoder-decoder chain more specific to the context, for instance, in this case, the data has different contexts in terms of weather conditions, in terms of complexity of environment, in terms of all these things, you can actually build a model that has multiple encoder-decoder, and every encoder-decoder pair is optimized for a specific context. And this allows you to essentially tune the compression better, and you achieve a much better compression or a lower complexity compared to just a general encoder. Okay, so we are moving with it, and you see there is something called context classifier that takes essentially the output of some intermediate layer of a first portion of a model, detects the context, and then decides what to do. This, by the way, is a trend, is a major trend in ML. You see this kind of multi-branch models, dynamic neural network, in sensor fusion, in different contexts where you want to decide the complexity of a model, how you do things. So models are becoming more aware of what's happening at the data level, at the system level. But we show that it works in this context as well. I'm not going to show too much the data, but I'm going to show you that this doesn't work only when you consider straightforward computer vision, but you can actually embed this logic, so compression and multi-branch model, in navigation. And when you think about navigation, things are a little more specific even, because if I think about, okay, computer vision, then I can reason in terms of how many objects I have, how complex, how big they are, the general context. But when I think about navigation, the task is not anymore a general computer vision task, is a control problem. And control problems do not necessarily care about the complexity of the image. They care about how complex the control is, right? So it's a little different. And I can make this example that you have a lot of tiny objects in the scene. From a computer vision perspective, that's very complex because I need to detect all the objects. I need maybe to understand the distance. I need to do many different things. Now, maybe from a control perspective, if I want to navigate, if everything is far, I don't care, right? So I can compress everything, just say, everything is far, and that's fine. So our problem here is a little different. We have a very simple navigation problem where you have a drone going from one point to another. The drone is taking RGB images and GPS to fly through the buildings. Now, you have an RGB image, and to navigate, you need some information about distance of object. So we build a chain, which is first a depth estimation model that takes the RGB camera and builds a semantic map with distance. Then we take the depth map, and we have a control layer. Okay, so there is a little bit of a pipeline here. Now, of course, we are splitters. So the first thing that we do is split. And we take the depth estimation model, and we split it, same logic as I show you. But now, instead of building one split only, we build many different versions, which is how much you compress. And you can control this by how big the compression point is, how you quantize. There are many different ways. I'm not going to go too technical today. But you can build this split part at the beginning of a depth estimation portion, and you build the pipeline through many different compression points. And then we call this the bomb model. For some reason, my students decided to draw it like this, like bombs dropping. But so we have now the depth estimation map, the depth estimation model, which is split. Then you have navigation model. And now, again, the same idea, which is you have an auxiliary model, which is controlling the shape that's taking, that the model is taking from a compression point of view. Now, there is a little bit of difference here. It's because this is a navigation problem, so you have a temporal dimension to it. And now we can use actually the output of the model itself to optimize the next iterations. We don't need to necessarily process information from the data, close to the data, which has higher dimensionality. So we have this auxiliary model, which is deciding, okay, given that I need to control the drone, how much information, how much can I compress? Okay, that's very interesting. By the way, the split model is really effective. So this is JPEG, and these are our models. You can go up to transmitting like a really tiny amount of data. We're talking about 1 byte, sub-byte information in some contexts. While JPEG, you see that drift at some point is just you need to transmit some data with JPEG. Okay, still this is low resolution, it's a micro drone environment. It's not too bad. And maybe it's not super clear here, but these are the different decisions that the model makes. And you see that the model is adapting the compression on different maps. You see that interesting thing that if everything is far away or very close, you transmit very small amount of information. And that's not because the information is less complex, it's because the control problem is less complex. Because if everything is far, I can use GPS and just go. If everything is close, no matter what, I need to go some other way. Mid-range, I need to plan because now I have a problem where I can go one direction or another. I need to navigate in between the buildings. Okay? And you see the model adapting to this. So this is one thing that we do. We are evolving this logic. We have been working on this for 7 years at this point. We have this in many different versions. We're now looking at joint fusion through splitting point or all these different things. But I want to just talk very quickly about another direction, which is this dynamic self-adaptive machine learning models. Okay, so this is trying to solve the problem of establishing the collaboration across the vehicles, right? But then I still have a problem of a complexity in itself. And that can be the primary vehicle, the secondary vehicle control. How do I make the algorithm as effective as possible, recognizing the fact that your control problem, again, is very different. It can be you're flying up high altitude in the blue sky. I mean, you don't need very sophisticated computer vision to do that. There is nothing around you. As you dive into an urban canyon, maybe you need to activate a little bit more logic for computer vision perspective and from a navigation perspective, right? Because now my problem is a lot more complex. There is another step on this, which is how I build the sequence of AI modules in different environments. That has actually one dimension in itself. For instance, do I need 3D mapping or not? That's a decision you make across the vehicles as well. That depends on where you operate. Okay. So just very quickly, I'm going to skip a couple of things, but there is one way of adapting neural models. So what I show you, which is multi-branch neural networks, that's one version of dynamic neural networks. You can have a module which is controlling the shape of the rest of the algorithm, right? But there are other ways to make models dynamic. One way is early exit. I don't know if you're familiar with that, but that's a way to control the depth of a model. You attach a smaller model at some point. If the process gets caught into that smaller model, then you're fine, and you stop execution. Okay, that's one way of doing this. Multi-branch is another way. There is another way, which is called slimmable neural networks, which is models that can adapt their width, right? So I'm gonna go very fast. The crash course is slimmable neural network is essentially you train one network, which can be slimmed. So you train the model, but the model can function even if you remove many of the nodes. Okay, and this is controllable. When this was born, not so long ago, it was basically as a way to train one model, and then at deployment time, you decide how complex you want it to be. But my problem is different. Is I want to actually adapt complexity at runtime, right? Because my problem is adapting the model to the context, not to the macro application, right? So we built a version of these models. I'm not going to explain how you train this kind of network. Again, it's all, by the way, everything seems very easy, but training the split models is actually fairly sophisticated. Not that many people who do that. Training slimmable neural networks is also like really hard. Like it sounds easy, but it's a little more like the way you train essentially a collective of networks using knowledge distillation, the sandwich rule, the way you train the weight. It's not easy to make this functional from many in many different ways. But now we want to use this in the same context as that we discussed in the split version, slightly different, a little simplified. So we assume we have a depth maps, right? For instance, you have a low resolution LiDAR. You have that one is pointing forward, one is pointing downward, and you want to make the navigation model adaptive to the context again. So we built a model which again has, you see, so this is actually a sensor fusion, strictly speaking, problem. You have two sensors, which is forward depth sensor, downward depth sensor, and GPS, but GPS, you always use it. And you concatenate them and you feed it to a navigation model, which is outputting where you go. But here again, we have an auxiliary model, which is deciding how slimmed, so how the width of this model. And there is one thing that is interesting, which is not only we are controlling the complexity of a model, but we're also, you see that we have a concatenation of different sensors. So the way we select which portion we activate here also reflects on which sensor we use. So this model is controlling how we fuse information, so which information we process, and also how complex the model is. Okay, so this is, by the way, is a 10-stage training thing where you use deep reinforcement learning, knowledge distillation, curriculum learning. It's really a mess to train. I have one very talented student who apparently knows it all and could solve this, but it's really, really hard. And what you get is very interesting because you get the same idea that we got in the splitting part, where again, here you see some maps with different complexity. This is simulation. We are now transporting it to it's a 3D engine rendering AirSim, basically, and with some improvements. And you see, like the color code is which sensor you use and what is the slimming of the different sensors. And we see the same thing here, which is if things are far away, you use minimal complexity and you use the sensor that makes the most sense. So forward or downward, depending where you are and where the objects are. If things are very close, the problem is again very simple because no matter how complex the image is in front of you, you just want to go away. If things are mid-range, you have maximum complexity because the planning kicks in and you need to figure it out. So this was very interesting. Now we are actually building on this to have a full chain. We are chaining some of this, the split and this to 3D mapping. So we are building the whole pipeline. And the pipeline, all the modules can be activated, deactivated, but also each module itself is adaptive as well. So we are going into full adaptive, collaborative decision-making. So that's the reason for doing this. By the way, there was one interesting result that we had some time ago is that you can actually train slimmable encoders, which means that you have a way to control the complexity of encoder. And this also has an immediate impact on the amount of data that you transmit. And quite amazingly, it works still. And you can actually build very effective dynamic encoders the way I mentioned. Okay. Now, and this, by the way, is runtime adaptive, which is where we want to go. So just 1 second about one of my maybe most dear results because it's closest maybe to what I used to do when I was a lot younger. Like, and my hair were a different color, and my daughter says, "Oh, Dad, your hair are the color of the clouds when it's about to rain hard." And I say, yeah, that's a better thing than the clouds when it's sunny, right? Because that's a white. Well, still, if it's about to rain, we're still in range. So there is one So especially with a PhD student, postdoc, I was focused a lot on the optimization of wireless protocols of, um, many different ways, from signal processing uh, to actual networking. And even now, I mean, a lot of what we do is focused on very simple communication-oriented metrics, which is traffic volume, right? For instance, if you have a 5G infrastructure that can adapt how much bandwidth is allocated to one specific set of applications, you may just want to reflect the traffic volume. But but bandwidth is never enough. And if you just think about traffic, you at some point very quickly you run out of bandwidth. When I started doing the split thing, I had all these wireless companies telling me, but Marco, why do you do it? I mean, we have so much bandwidth with 5G. There is no problem. We just transmit 1 million megabytes per second. There is no problem. And I say, okay, that's fine. And then, 3 years after, they came back and I say, Marco, edge computing doesn't work. What do we do? And I wanted to have this, thing at the entrance of my office that says edge computing in 5G doesn't work. And the reason is that no matter how much bandwidth you have, you don't scale. Like, you want to transmit high resolution videos, there is only a certain number of that is financially viable. And yeah. So, but the general problem with that is that you don't want to reason just in traffic volume. You want to start to reason in terms of semantic. So as I told you, like, there is a certain reflection between what you see in terms of complexity from a computer vision point of view and from a control point of view. So the amount of data the bandwidth, the resources that you allocate should also reflect the data and the mission. So the general problem, which is very trendy in the communication aspect, is making communication and networking semantic. Okay, and this takes many different meanings. Sometimes people just mean you transmit semantically compressed data, which is what I explained to you. But to me, is actually how much resources do I allocate given the mission, right? If a drone is flying the blue sky, it should transmit less data, but maybe the data should be less prioritized, for instance. So this is all, it's all connected in a way. I'm not going to explain too much about this because I ran out of time, unfortunately, but we did quite a bit of testing with the rovers, and the rovers have these multi-antenna routers that you can actually control how many streams you have, how you connect, how you packetize information, how much bandwidth you use. And so the problem is, how do we allocate resources in terms of a mission of a rover? And we started with a simpler problem, now moving into more like 3D mapping and splitting. But we started with a problem of understanding the environment, having different tasks. And so if your problem is detecting objects or segmenting an image or classifying an object, or you can think of this as different levels of complexity of the task itself, right? Semantic segmentation is so you want to have essentially the same image, but with labels per pixel, right? So now at the end of this, you have an image. So you can imagine that this is a little more difficult than, telling a pizza from a hamburger in a whole image, right? From a communication perspective, that means that you cannot lose packets. You need packets in time to build your pipeline. So if you think about packets arriving too late, packets that do not arrive, all these things, you want to push the problems on to simpler tasks, right? So you can actually build a control problem on top of this and actually build a little agent, a minimal complexity agent that, first of all, detects the context. So am I have a lot of buildings, am I in line of sight? So I have an empty scenario. So that's just to understand how the channel behaves. And then the communication link behaves. And then we have a little agent that is also extracting the semantic of the task and the complexity of the image, and is deciding how much resources to use. Right? So this is very simple, but we are now trying to push this to actually understand how much data we need to for 3D mapping, for the control of a rover, where we split the pipeline. So there is a very deep connection between how you compute and how you communicate in these kind of systems that shouldn't be ignored. Okay. And again, this is, I'm giving you this example. I can give you healthcare related example. I can give you, most applications are like this. I work in healthcare, edge computing communication for healthcare for almost the same amount of time, maybe more actually. And you have still the problem of a small sensor, a phone, and transporting the data over Bluetooth, and you want to reduce the amount of data that you send. You have minimal complexity, you have unreliable channel, you have multiple. So you want to select the data, you want to remove some data, you want to compress the data. Similar issues from a point of view of a different scale of a problem. Okay, so I'm not going to show results. I'm already very late, but I hope at least I deliver the message that there is an intersection that needs to be explored, maybe a little deeper in terms of algorithms, computing, application, and communications. And it's very important to not just think about the different components, but think about how they interact and how they intersect and trying to build something that works. And again, in my experience, there is no commercial version of this that actually works. And just transmitting videos, just transmitting, I have a startup too, like I confess it. And when we talk about this, people still say, why do you compress the data? And then we realize, okay, if I send a high resolution video to an operator, that doesn't scale or it doesn't work in many settings. And then you talk with the engineers and they say, okay, our range is 50 meters in a forest. And I say, well, yeah. So where is the guy? Is the forest or, and there are problems like this everywhere. And even when these kind of things work, then you think about sensor fusion, which is very important. You cannot just have videos. If you want to be operational at night, you need to have LiDAR. You need to have data that are incompressible with standardized methodologies. So I hope at least I conveyed the relevance of this and how we approach the problem. And now I'll leave some time for questions. Stop recording.